Hi, I'm Charlie Thompson, and welcome to Human Geography for spring of 2021. In this video, I'll go over the first chapter and cover most of the main points of human geography, which is really saying a lot. Human geography is huge, geography is huge. You'll see. So what is geography? That's a heck of a good question. This is a horrible definition, and yet it's also a really good definition. It's just got way too many words. But the study of all the interaction of all the physical and human phenomenon at places and how interactions among places form patterns and organize space. So geography for me is the way I understand the world. It's the way I make sense of the world. Physical geography helps me understand why some places are hot, some places are cold, some places have pine trees, some places have deciduous trees, some places have cactus. And human geography helps me make sense of why they have different languages and religions and architecture and clothing and food in different places, why some countries are rich, why some countries are poor. All of that is part of human geography. So the study of the interaction at places, so the physical and human phenomenon that make up a place, and also then we're studying relationships between places that form patterns. So that's a pretty good definition of geography. It's really long, it's really technical. Take a look at the Wikipedia article on just what is geography. It's a good place to start also. Another definition, anything with a map. Geography is a spatial science. Geographers tend to be very concerned with where things are in relationship to other things. Where are they now? Where did they used to be? Did they used to be here? Are they not here anymore? Anything with a map, if you can ask a question, if you can answer a question with a map, congratulations, you're doing geography. Perception. People's perceptions. Part of geography is perception. Behavior. Geographers get to study human behavior. Oh man, this is like a 20-year-old graphic now. It was super cool. This was the architecture of the internet. And let me grab a pointer. There's a good pointer. So these white lines are the fiber, well, from 1990 or whenever this graphic was made. These were the fiber optic backbones of the internet, the main connections between places, and then from each of those nodes, making connections to local areas. So looking at this, I don't know, it was interesting once upon a time. It's kind of interesting now. If we were in class, I'd probably spend a couple minutes and talk about, or rather ask you to tell me about, what patterns do you notice? So pattern, and I'll talk about the definition of pattern or what we mean when geographers talk about pattern. But one of the cool things about maps is often with a map, you can see patterns that you can't see from a spreadsheet. So it looks like the West Coast has a lot of connections in Silicon Valley and the Pacific Northwest, Microsoft, the East Coast with universities and Wall Street, a high density of fiber optics, and then the flyover states in the middle of the country, not a whole lot of fiber optic backbone connections going on there because there's not a lot of people there. So patterns, maps, old graphics. Geography is the study of spatial. Spatial means space, like where is it? And temporal is time. So it's the study of relationships of space and time. Where are they now? Where did they used to be? Where are they going? That is a big, important theme in geography. Oh, yeah, like this. I just found this map on the web from the Reddit, I think, map porn forum. So this is a map. It's a modern map that was made using ship's logs from the 16 and 1700s. So in navigating a sailing ship, back in the day, they kept track of where they were minute by minute throughout the day. And somebody took all of those logs, those books, and figured out exactly where the ships were and then plotted them out. So this is the British East India Company. They're the red, the Hudson Bay Company in this magenta, Dutch East India in blue, I don't know, another Dutch company in yellow, somebody else Swedish East India Company in that purpley color. So you can see the general patterns of where trade was being conducted between Northern Europe and the rest of the planet. And he also broke it out. So we've got all points and then by nationality. So England, and that would be the British East India Company. So we've got the British East India Company and where they were going. Oh, also the Hudson Bay Company going to Hudson Bay. Spain, almost entirely in North and South America. France, almost entirely in North America, except for the Caribbean, Haiti. And then the Netherlands, heavily in, well, going to Africa, and then also Indonesia, which was for a long time a Dutch colony. So in this map, we can see where different nationalities were going. Oh, and then it would be really interesting to see a map of the trading locations, where they were going. And then later, we'll see how hundreds of years later, this results in patterns of religion, like Catholicism throughout the Americas as a result of Spain and Portugal, as opposed to Protestant Christian religions in, for example, South Africa, the United States, as a result of the British, and then Catholicism in Quebec with the French, the remnants of French culture there, and also in Louisiana. So looking at something that this data is from the 1600s, but 400 years later, the patterns of language and religion and probably also commerce are still intact. So this is a good example of patterns. You can see very easily where the Netherlands, where ships were traveling out of the Netherlands, France, Spain, England. Good stuff. Development of modern geography. Early geography tended to be descriptive. In the Graves text, he refers to this as like trivia. These are the National Geographic articles about focus on Kansas, and they talk about the climate and the religion and the language and the agriculture and the economic activity. That's just describing what's there is descriptive geography. Later, Karl Ritter and Alexander von Humboldt, two important German geographers in the 1700s, started asking questions like, okay, what does it mean? What's the significance? Why? Why do they speak that language there? What does it mean? Why is Indonesia, why is Indonesia the largest Muslim country in the world? And what is the significance? So the early geography tended to just be describing what was there, which is a pretty good place to start. But then later, analytical and critical geography started asking questions. They looked at human-environment relationships. Graves talks about environmental determinism, for example, an idea that is no longer accepted in geography, that culture is dictated, is determined by the climate. We have a much more sophisticated understanding of the forces that drive cultures. Environmental determinism, there you go. So in geography, in studying geography, I just look at it as geography. However, we don't have just one huge 400-unit class that's geography. We have human geography, that's this class. We also have physical geography lab. So our classes pretty much follow the big split, the big division between human and physical geography. So here's a chart of different types of geography. Over here on the physical side, we've got looking at climate and landforms and soils and plants and animals. And then over on the human side, we have behavioral geography, economic geography, behavioral geography, people's perceptions. What landscapes do they find attractive, or what landscapes do they find threatening? Economic geography looks at prices of land. Where do you site a factory? Where do you open up a new Starbucks? All of those are economic factors. Historical geography is really just like history, but with more maps. Like at this point in my life, I think of history as geography without the maps. Historians tend to be concerned with when, the temporal aspect. Well, this happened and then that happened. Whereas geographers tend to be more concerned with where and how did that affect what happened. So historical geography would be talking about, for example, one place and looking at different groups of people coming in over time. Marketing geography, yeah. How do you market to people? Political geography, we will spend an entire chapter on. There's names for the different shapes of countries. I don't find that super interesting because there's not a whole lot you can do about it. If you're an island nation, not a whole lot you can do to become more compact. Political geography, we'll talk about gerrymandering, which is when you take away a group's votes by dividing up the blocks that the people vote in, the tracts, the precincts. And then population geography, looking at population over time. So human geography is a social science, physical geography is a physical science, except there's no part of physical geography that isn't affected by humans, and there's no part of human geography that isn't affected by physical geography. So geography really, the key to geography is power. The power of geography is a holistic view, that it looks at all the parts and how they come together to create whatever it is that you're trying to study. So geography takes a very broad view and also a detailed view and looks at how the individual parts work together to create the whole. And then other subsets like urban geography, that actually I would put urban geography up there. Medical geography. This is one of the most famous maps from geography. Obviously it's a reproduction of the original map, but in the 1850s in London, they had cholera outbreaks. Cholera is a waterborne disease. It's a very deadly disease. This one particular outbreak killed over 500 people throughout London. And this one doctor, Dr. John Snow, started mapping the locations of people that died. Those are the red dots. Each dot is one death. And then also the water pumps. They did not have running water in England in 1854. They had public water pumps. And so what you do is you'd go to the water pump, you'd fill up your bucket, and you'd bring it home. You'd use that. In the morning, you'd wake up and go to the bathroom into a bucket, hopefully a different bucket. And then in London, in many cases, and by this point, people were living in apartment buildings, basically multi-family dwellings. So a whole bunch of families in an apartment building. And you go to the bathroom in the bucket and you don't throw the waste out the window. You take it down to the basement and dump it in the corner on the dirt. That was their plan. And I always wonder, what were they thinking? I mean, the liquid stuff would soak into the ground, but your basement would just be disgusting. That's no way to live. And yet they did. Today, we have nuclear power plants. There's absolutely nothing we can do with nuclear waste where it will be safe longer than it's dangerous. That spent nuclear material is going to be deadly for hundreds of thousands of years, and there's no place that we can put it. And yet we keep making more, even though renewable electricity is the cheapest way of making electricity. So all kinds of groups of people throughout history have made really, really bad decisions. In this case, back to the cholera outbreak, Snow, and this is also an example not only of medical geography, but of the power of maps and patterns, which I've talked about before. So Snow realized, oh, there's a concentration of people, of dead people, around the Broad Street pump. Snow's suspicion was that the Broad Street pump had been contaminated because after you throw your waste into the corner and it sinks down into the ground, it sinks into the groundwater and then you're pumping it back up. So all these people that had cholera were then dumping their waste. It was soaking into the ground and contaminating the pumps. So they shut down this pump and the cholera outbreak went away, which obviously is a short-term fix because the long-term problem of lack of sewage facilities and lack of clean drinking water still was a problem that they didn't solve for many years. But back in the day, this was an outstanding use of early medical geography to shut down a pandemic. A more modern version of a pandemic. It's interesting. So just last year in spring of 2020, I just was looking through my announcements, and on March 11th, that was the last day of class I held, because I had been tracking this since the beginning of the year and watched the cases go from, in the United States, from 60 to 6,000, and it just kept going up and up and up. And so because I'm a geographer, I said to my students, we're not going to meet anymore. There's this disease and there's no vaccine and there's no cure and it's airborne. So we're out of here. The school says we don't have to come to class anymore. We're not coming to class anymore. I will try to find a link to a software program that I found around this time, a software program that allows you to simulate a pandemic. It's kind of like that the zombie game where you try to infect the whole world, except this is you try to save the world. But it actually uses geographic data. So it knows population centers, it knows airports and train stations and how many people come through those areas. You can specify different behaviors for the disease. Is it airborne? Does it spread through physical contact? How infectious is it? So modern medical geography right now, looking at COVID-19, one of the hot topics in geography, and also one of the topics that we'll spend time on this semester, because COVID has had profound spatial changes, lots of spatial changes. People's spatial footprint got smaller, people traveled less, carbon dioxide emissions decreased because we weren't traveling as much. Big geographic ideas. Let's look at some big geographic ideas, some geographic themes. We got the human versus physical. That's a good one. Regional versus thematic. So this applies to different approaches to studying human geography. So regional versus thematic, two different ways that you can study human geography. The regional approach is to look at one region at a time and analyze all the aspects of that region. So you could look at the Central Valley, you'd look at the physical landscape, you'd look at the climate, you'd look at the soils, you'd look at the population, you'd look at the ethnicity, languages, religion, economic activity, agriculture in one region. So the regional approach, you look at one region, all the themes, one region. It's an old tradition. Bernard Veron was a geographer in the late 1600s who said these are the appropriate topics for regional studies: the stature of the natives, employment, virtues, vices, learning, and wit, customs, cultural geography, speech, language, politics, government, religion, cities and famous places, history, and famous people. So we're going to tackle most of these. Although we're not going to have a regional approach, we're going to use the thematic approach, which I'll talk about in just a second. But we're going to talk about employment, economic activities. We're going to skip virtues, vices, learning, and wit. Customs, that would be culture. Speech and language, we'll talk about. Politics, we'll talk about. Religion, we'll talk about. Urban areas, we'll talk about. We'll skip history and famous people for 500. But you can see many of the topics, they're old topics. Thematic geography looks at one theme, so religion. How is religion expressed differently in different regions, and how does that influence the culture? One of the proponents of regional studies was one of my geographic heroes, Carl Orntwin Sauer, an American geographer. He went to the University of Chicago and then later taught at the University of California at Berkeley. And he came up with the idea of the cultural landscape, which is, I think, one of the most important and one of the most powerful ideas in geography. So I mentioned that for me, geography is just the way I make sense of the world. And Sauer's idea of the cultural landscape is an important part of that. So Sauer said, each place has a unique landscape. Davis is different than Woodland, is different than West Sacramento, even though they're, approximately similar in their population sizes, but culturally they're all very different. The reason each place has a unique landscape is because we start off, every place starts with the physical landscape, but then it's modified by human interaction. So the cultural groups then would be the different people coming into different areas, coming in at different times from different regions with different ideas. And that helps to explain why each place would have a unique landscape. If we were in class, in fact, I'll probably just give you an assignment about the cultural landscape to find two places that might be similar in some respects, but different in other respects, and then try to interpret and understand those places through the idea of the cultural landscape, that each place has a unique landscape. And the reason each place has a unique landscape is because the physical landscape was modified by human interaction. So it's the interplay of the physical landscape and human culture that then creates unique landscapes. Survey systems are part of that the French had a long lot survey system that they used. They divided up the land for ownership into these long strips. The British had a system called metes and bounds that had land deeds linked to actually features like rocks and trees on the landscape. And in the United States, we used the square, township, and range system that was developed by Thomas Jefferson. So the group of European colonizers that settled in a region and surveyed the land divided up the land into different shaped chunks. So even just looking at aerial imagery, remote sensing imagery, if you showed me this picture, I'd say, oh yeah, that's the French long lot technique. So here's a big chunk of land, and when this guy dies and the land passes to his sons, if he has two sons, they would cut it in half. If they have three sons, it would get cut up into three strips, and so on and so on. So eventually you end up with these little tiny narrow strips. And I think it is because everybody needed access to the river. This used to be the main channel of the Mississippi River. It got cut off in 1722. But up until 1722, this would have been how you'd bring goods to market, is shipping them down the Mississippi River. So the French long lot technique. Here we've got the British metes and bounds, irregular polygons defined by natural features in the landscape. And then our system just divides everything into nested squares. Toponym. Toponym means place name, and you're going to have an assignment next week looking at toponyms in the landscape. Topo means place, and nym is name. It's a fancy word for place name. But toponyms are really cool because they tell you about the people that named the places in an area. They can tell you about the physical setting. Red Bluff, for example. They can tell you about political changes. For example, in Iran, after the Islamic Revolution of 1979, places that had been named after the Shah of Iran were renamed for other people because they hated the Shah. Most places in the United States, many cities in the United States after the death of Martin Luther King Jr., renamed one of their important streets MLK Boulevard or MLK something. So that's an example of political changes. Social customs, for example, the presence of Catholic-based place names in California tells us a lot about the Spanish that named them, what was important to them. So here we have Catholic place names in French-speaking Canada. This is a place called Naughty Girl Meadow. It's in Idaho, and it's important. It's amusing, and it's also in a book written by a man named Mark Monmonier. I'll drop a link to that in this unit's materials. But Mark Monmonier is a geographer, also from the University of Chicago, and he's very interested with toponyms. One of his book is From Squaw's Tit to Whorehouse Meadow, which brings us back to Naughty Girl Meadow. So this was called Whorehouse Meadow, and the good people of Idaho were ashamed of the name, and they appealed to the U.S. Geologic Survey to officially have the geographic name changed from Whorehouse Meadow to Naughty Girl Meadow, which I would say is slut-shaming. And it's inaccurate that it was called Whorehouse Meadow because that's where, in Idaho, this was a region, economic activity was sheep ranching, and sheep need to get their wool cut off so that the wool can be made into fiber and then fabric. But once a year, the shepherds would bring their sheep to Whorehouse Meadows. And it was called Whorehouse Meadows because sex workers would come and set up shop to make money off of the shepherds who were coming in to get their sheep sheared for the season. So Whorehouse Meadow is an accurate name that reflects the economic activity that happened there. Naughty Girl Meadow, I don't know what that means, but in the book From Squaw's Tit to Whorehouse Meadow, Mon Minier talks about offensive names in the United States. In fact, in Sacramento, we've got Negro Bar. Negro Bar hasn't always been called Negro Bar. There's another feature there's many features. In fact, there's a website, the USGS has an online database that if you put in a term or a name, you can see a list and the location of all the places in the United States that are named. Like there's a Thompson Bay, spelled my way, Thomsen, in Alaska that I was unaware of until I put it into the Global Name Information System lookup at the USGS. But on the Sacramento River, there are many features. There's a Negro Sam Slough, and I wanted to use it for one of the labs that I did, and then thought, I don't want to do that because on the old map sheets, it's not called Negro Sam Slough. It's an older, much more offensive term that was used at the time. And so I didn't want to have an offensive lab exercise because once upon a time that feature had an offensive name. But toponyms. So we've got Naughty Girl Meadow, Floyd's Knobs, either in Kentucky or just across the river in Ohio. I just thought it was funny. Region. So one of the ways that geographers make sense is by defining. So you as the geographer are defining the region, its area that you're going to study. And there's different ways of defining regions. So there's different regions based on how they're defined. The regions, they're just an idea. You are the person who's saying, I'm going to study the Sacramento Valley, and the region that I'm going to call the Sacramento Valley extends from the Delta north to Red Bluff. It's going to extend east-west across the Central Valley. Whatever those limits are, that's what those boundaries are they're often artificially created by the person who defines the region. So that's what I mean by it's just an idea. I mean, the Central Valley, it's really there, but if we're drawing lines on a map and we're going to call it a region, that's an idea, not the place. The way we think about the place is the idea. So there's three types of regions. There's formal, there's functional, and vernacular. So formal regions, everything in that region shares at least one characteristic. So California is a formal region. Everything inside California is inside California. This is a functional region. The way I remember it, I'm not very smart, so I use a lot of mnemonic devices to help me remember things. Functional regions have a focus. So this is a super old map, and it's broadcast television stations, and close to the transmitters, most of the people watch that station. As you get away from it, fewer people watch that. So functional regions have a focus. So most of the people around Des Moines are watching the local NBC station for Des Moines. Newspapers also have a similar pattern, a functional newspapers. The people who subscribe to the Sacramento Bee, most of them are around Sacramento. So there's a concentration, and then as you get away from it, the numbers decrease. Vernacular, different ways of defining the region called the South. The black line is traitorous Confederate states. The red line, fewer than 50% high school graduates, that just frightens me. Just thinking about how much I knew of the world when I was in my sophomore year of high school. 50% Southern Baptist, we've got a religious one. Cotton producing area, winter precip, the dotted line, last frost in March. So The dark green areas meet all 6 definitions. The lightest regions only meet, is Texas part of the South? I don't know. Texas is weird. Florida? Maybe? I don't know. So vernacular regions are based on people's perception. I think vernacular regions are the most interesting, the most fun. Because of that reason, it's just based on people's perception. For example, NorCal versus SoCal. So here they've just got a blue to yellow gradient going on. And they're using as their criteria like, dude, the city, and hella. That most of the people who say hella are in the North State. People who say like and dude are in the South State. Northern California people tend to refer to San Francisco as the city. So that's one vernacular way. One way of looking at California or NorCal and SoCal as vernacular regions. I also found this a more exhaustive population. Half the state, half the people in the state, half the people in the state. Geography, surveys, climate, dry versus wet, sports teams, who do you root for, different attempts to divide up the state. We could zoom in a little bit more. So they just kept moving the line south until they got half the people north and half the people south of that line. Survey where people think NorCal and SoCal is. That looks pretty good. Freeways. Freeway names. I would like to see a map of freeway names, because in Southern California, where I grew up, we would say, for example, you take the 23 to the 118 to the 5, and all the freeways that I learned when I moved to Northern California, they're 80. It's 80. There's 80. There's 113. So if I was going to go to Southern California, I'd take 113 to 80. I'd take 80 to the 5, and then I'd take the 5 to the 118 to the 23 to the 101. So vernacular regions, it's just based on people's perception. Bay Area, I was going to say, I'd like to see a map of that, of businesses. In fact, one of the ways they used to do this, when they had phone books, you could be a geographer looking through the phone book and looking at the geographic names of businesses to get an idea of what people's perception of their vernacular region was. There's places in Sacramento that are Bay Area whatever, Bay Area Auto Parts. I don't think Sacramento is being part of the Bay Area. More developed and less developed countries, another important region. I don't know what I was doing with that. So more developed are going to be North America, Western Europe, South Pacific. Depending on who you're talking to, often they'll include China and Eastern Europe in the more developed countries. Sometimes they don't. Japan, Australia, New Zealand, North America, or the United States and Canada, always there. Western Europe, always there. Eastern Europe and China, depends on who's making the map, right. So this goes back to what I said before, is it's just an idea, right? So some geographer, I think this is from Knox and Marston's textbook, they decided that based on their criteria, Russia and China were not part of the more developed countries. Another geographer looking at a different criteria for more and less developed would probably draw that line differently. Okay, spatial distribution. How are things laid out? Where are they in regards to other things? So this is the new vocabulary. Geography has a lot of new words, a lot of new ideas, but a lot of new words. The 3 things that we look at: density, concentration, and pattern. So let's look at some examples. So we've got 3 different, it looks like the same landscape with 3 different possible configurations. In terms of density is the number per area, like people per square mile or houses per square mile. That would be density. So this density is half the density of this. These two have the same density. They have the middle and bottom images have the same number of houses per land, so the density is the same. but the pattern is very different. This, all the houses are along one side of the street. All the houses are on one side of the street. The houses are just kind of scattered around. So the density is the same, but the pattern is different. And then concentration is, that's like the density within an area. So both of these, right, if we took all the houses and we just put them into this little tiny area, this plot and this plot would have the same density. They would have the same, let's just say it's 1 square mile. Let's just say they've got 40 houses per square mile, 40 houses per square mile. But this, you can see the houses here, they're much more concentrated. And if we squish them into a smaller area, they would be even more concentrated. So concentration is kind of a weird, it's like subdensity. It's the density within an area, if that makes sense. Patterns. I keep coming back to this of patterns. So these are the locations of the Nippon Denso Automotive Corporation. And they are typical. The pattern for this corporation is typical that the headquarters are in a more developed country, in this case, Japan. You can see the headquarters and research and development and some of the manufacturing in Japan. It would be interesting. This is from 2005. Oh my God. It'd be interesting to look at a new map to see where they are now. I know that in the past there were requirements. For example, I think you had, if you're buying a remanufactured engine for a Japanese car in Japan, it had to be remanufactured in Japan. So there might be some laws that dictate, like if you're a Japanese auto parts store, you can only sell parts that have been made in Japan. And it's weird, though, to have manufacturing, which is a low-wage job, being done in a more developed country. I would assume that over time, many of these manufacturing plants have shifted production to less developed countries where they can pay the workers less money, and therefore it's more profitable. So again, the pattern, the headquarters, research and development in a more developed country, and the manufacturing, I would assume, would be done in a less developed country. Patterns, we'll talk about this. This is Chicago. And now we're looking at patterns of ethnicity and race. These areas, at least 99% African American, 99% white. And then this boundary or border area, that's an 80-20 split, 80% white. And I think it's interesting that in Oak Park has always been a diverse, interesting neighborhood. Hemingway lived in Oak Park. Scott Fitzgerald lived in Oak Park. Oak Park has always been mixed, and it always makes me wonder. I'd like to go back and look and see who was living here. So we know that there's African Americans. 20% of the population was African American. I'd like to know the economic. I'd like to know more socioeconomic. Were they African American doctors and lawyers and wealthier African Americans that were living in Oak Park? Berwyn, the enclave of Berwyn. So this is CTA. So this is light rail. This is light rail. This is light rail. That's light rail. There's light rail. But you can see the light rail doesn't go to Berwyn. They had no interest in letting poor people who would take light rail go through Berwyn. And it's also interesting that the city limits are shown in red. Redlining is a racist practice of only selling to people of a certain race and not selling to people of other races. So in the United States, the way this played out was minorities would not be shown homes, would not be allowed to buy homes in Berwyn or Cicero. That's the way you have that exclusionary housing. Sacramento there was redlining present in Sacramento, and when we get to the chapter on race, we will be looking at redlining across the United States. It turns out to be incredibly important in economics. The economic history of the United States, redlining was a very important part in the post-World War II accumulation of wealth. If you were white and you could buy a home, you generated wealth as your house got more expensive over time. If you're African American, you couldn't buy a house. So even if you had the money to buy a house, you were still renting, and so your wealth didn't increase. We'll take a look at that. Diffusion, how things spread around, right? We know that things don't stay where they started. Otherwise, French fries would only be in Belgium and Belgian waffles would only be in wherever they are actually developed. So diffusion starts from a hearth. The region or place where something starts is the hearth, and then it spreads out, and there's a couple different ways that things spread out. So expansion means that the numbers of whatever are increasing. So like McDonald's, right? They started with one store, and then through franchising, they got more and more and more stores. So because the numbers are increasing, that's expansion diffusion. There's a couple different types of expansion diffusion. There's hierarchical diffusion. So that's when a hierarchy exists. For example, cities that are getting really big metroplexes or cities that are getting major sports teams are going to be big cities. You're not going to find a 20-screen theater in a town that only has 5,000 people. So the diffusion of multiplexes is going to be hierarchical because in order to keep that theater open, you've got to have enough butts in the seats. And the only way you do that is to have your multiplex in a big city. Contagious means it's just spreading from one place to another place without any sort of hierarchy. And relocation is the third type. Expansion, relocation are the two general categories. Hierarchical, contagious, and relocation are the three types of diffusion. Relocation means that the people just moved someplace else. So the numbers aren't necessarily increasing, but the spatial extent is. So for example, after the Vietnam War, Hmong refugees coming out of Vietnam and Thailand came to the United States. So their spatial footprint is much bigger because some are in Asia and some are in North America now, but the numbers didn't necessarily increase. So I'm going to say for the way I've explained that example, that's a good example for relocation diffusion. So here we've got baseball teams, Major League Baseball teams with the expansion teams, which answers so many confusing questions like the Giants and the Dodgers, they used to be Brooklyn. Why are they here? Why do we have the New York Giants and the San Francisco Giants? Well, because the football team stayed there, but the baseball team moved out of New York to San Francisco. So that would be hierarchical because not every city is getting a major league team. Only the cities that have a large enough population to support a major league team are going to get a major league team. We could probably look at the same thing with Major League Soccer across the United States. So this is hierarchical diffusion. Looking at the spread of AIDS across the United States, I would also say that this is hierarchical. The cities, or rather the states that had the highest rates in 1993, California, Nevada, Texas, Florida, and New York, also Massachusetts. That's Long Island, so that doesn't count. Jersey had a high rate. So those would be states that had large metropolitan areas, large enough cities where people with AIDS were moving out of places like North Dakota or South Dakota and moving. So that would be relocation, right? Because the people moving from one place to another, that would be relocation. Although the relocation diffusion was being done in a hierarchical manner because they were moving from small towns to large towns. And I think Graves refers to that as reverse hierarchical diffusion. This is not a clear-cut example of anything, which makes it an excellent example for complexity. That the books, geography books, I suppose all textbooks, really often present an overly simplified view of what's actually going on. Reality often is way more complex, but to fully embrace the complexity would take way more time than we have in several semesters. So we'll just keep it simple and say, well, you've got contagious diffusion within cities. You've got reverse hierarchical diffusion of people moving out of small bigoted towns moving to larger, tolerant cities. That would be reverse hierarchical diffusion. So we've got contagious, we've got relocation, we've got hierarchical. We've got everything. Looking at Delta Airlines, their major hub is Atlanta. They've also got hubs in Cincinnati and Salt Lake City. I wish I had a Southwest, because the joke about Southwest, you can fly any place you want. I'll make the joke about Delta. You can fly any place you want as long as you don't mind going through Atlanta first. So yeah, you can fly from LA to New York, but you got to go to Atlanta. And this would obviously then be hierarchical, because Atlanta, Dallas, Cincinnati, Salt Lake, major cities in those regions. Maps. So one of the ways geographers do geography, one of the tools geographers use to do geography, are maps. One of the important aspects about maps is map scale. Map projection, another important topic. Latitude, longitude. How do you find where you are? Latitude, longitude. So scale is the size of the map, the ratio of the size of the map to the size on the ground. So these two maps are both showing Singapore. That little dot right there is Singapore, which is this entire map. This is a large scale map. Large scale map has a lot of detail of a small area. This is a small scale map. It has small detail of a large area. Small scale map has a large area. A large scale map shows a small area. A large scale map, it's like you've zoomed in. Small scale map, you've zoomed out. And again, so this is a 1 to 10 million scale map. And then zooming in 10 times, we've got a 1 to 1 million. Zooming in 10 times, 1 to 100,000. Zooming in 10 times, 1 to 10,000. So this is the smallest scale map. This is the largest scale of these four. But as you can see, there's no such thing as like a perfect map, the best map. It's just, what do you want to see? What are you trying to show? Are you trying to show the location of all of the cities on the Florida Peninsula? That's the map you want. If you're going to Miami and Fort Lauderdale and you wanted a map of that region, that would be your friend. If you wanted a map of just the general Miami region, this would be your friend. And if you're, let's say, going to a geography convention and you're staying at the Hyatt Regency and you're walking around town, this would be the map that you would use to see, well, how do I get from the Holiday Inn or the Hyatt to the convention center? This is the largest scale map of the smallest area. This is the smallest scale map of the largest area. So in this example, we're not just zooming in, but the data is being analyzed at different scales. This is an incredibly important point. So in this map, which is the smallest scale, the data is state by state. Each state is the same color across that state, right? So for Oklahoma, we've got the data for Oklahoma. And now we're looking at the Washington, Baltimore metropolitan area. I think these are counties. And then just looking within Baltimore City, we're now looking at individual zip codes. So all of these maps are looking at deaths from cancer per 100,000 people, Baltimore City, the Washington, Baltimore metropolitan area, and then the entire United States. So at each step, there's different patterns. Like you can see the linkage between the Mississippi River and rates of cancer deaths. On this, you can see that across the Washington, Baltimore, the Washington, Baltimore metropolitan area. BOWASH is Washington to Boston. Sorry, my bad. You can see the patterns across that region. And then within the city, there's patterns. And then that leads rise to really sophisticated cartographic questions, such as, is the way that the data is being mapped at giving us an artificial idea of what's going on? Like, probably the rate isn't uniform throughout this entire zip code. So if we could break it down at a larger scale, if we were to zoom in and look at, if we mapped out the people and made a dot map for the people like the Jon Snow map, we'd get a totally different pattern than this, I would be willing to bet. Because it looks like there's some coordination between the cancer, or correlation between the cancer rates and the freeways. And it might just be artificial because of the shapes of the zip codes are leading us to that false conclusion. But without more data, we don't know. So again, just to back up and say what the hell I'm trying to explain, Looking at mapping data at different scales can show you different things. So the same data just mapped out at different scales often looks totally different and can give you answers that you didn't know you would find. Locations and time. So now we're talking about latitude, which is going north or south of the equator. Lines of latitude are called parallels. So these are all parallels of latitude. It goes from 0 degrees at the equator to 90 degrees north, because it's really an angular measurement. It's a measure of the angle between the equator and wherever that point is. So if it's a 49-degree angle between the equator and that spot, if we connected up all the places that are 49 degrees north, that would create the 49th parallel. You can see the parallels, they're parallel, but they're all different lengths. Like the North Pole is just a dot. The longest parallel is the equator. Some geographic zones. The tropics are from the Tropic of Cancer to the equator to the Tropic of Capricorn. Tropic of Cancer, 23.5 degrees away from the equator, because Earth's axis is tilted 23.5 degrees off of vertical. We've got the subtropics, the mid-latitudes. That's where we live. In fact, most of the people on Earth, I think, live in the mid-latitudes. The subarctic, and then Arctic. Latitude is incredibly important. It determines day length. Day length on the winter solstice. No sunlight on the winter solstice. Over 10 hours of sunlight on the winter solstice. On the summer solstice, these white areas are above the Arctic Circle, so they're getting 24 hours of daylight. We go from like 14.5 in the summer to just about 9 in the wintertime. That's our shift in day length from summer to winter. This is just showing ultraviolet light and the greatest concentration of ultraviolet lights in the tropics at high altitude, because there's less atmosphere to filter out the ultraviolet light. So yeah, you can see it's primarily over the oceans. It's just a function of latitude, but over the land it's latitude and then altitude, with these higher elevations being higher amounts of ultraviolet light, which causes skin cancer and skin damage. And so in response, our bodies create melanin, a pigment. And so we've got, this is showing of the indigenous populations of the world, what their skin tone is. Ultraviolet light, skin tone, good times. Another map showing the same thing. So really, skin tone just tells us where your genes have been for the last, 100,000 years or so. 50 to 100,000 years. I think Australians have been in Australia someplace between 40,000 to 70,000 years. Longitude is your distance east or west of the prime meridian. The lines of longitude are called meridians. They're all the same length. And it's your angular distance east or west of the prime meridian, which runs through Greenwich in England by international agreement, decided in 1884, because the British were the first country to have people that could make a clock accurate enough to keep time in the open ocean. If you have 2 clocks aboard your ship, you can calculate your longitude. Earth rotates 360 degrees in 24 hours. So in one day, Earth makes a complete rotation. Earth rotates through 15 degrees in 1 hour. So if you knew what time it was in Greenwich and you knew what time it was where you are, you just divide the number of degrees and you can find out your longitude. If you're 1 hour away from Greenwich, then you're 15 degrees. If you're a half hour, you'd be 7.5. If you're 2 hours away, you're 30 degrees away. Super simple. The hard part was making a clock. And this clock wasn't manufactured. This was handmade. This clock was handmade in the late 1700s. So it wasn't until, just over 200 years ago that Europeans knew their longitude. Finding your latitude, let me back up. Finding your latitude is easy. If you can see the North Star and you're above the equator, the angle of the North Star to the ground is your latitude. So people have it's really easy to find your latitude. If we went out tonight and I showed you where the North Star is and I gave you a protractor, you'd measure it and you'd find, oh yeah, the North Star is about 40 degrees above the horizon. The angle of the North Star to the horizon would be about 40 degrees, and that's your latitude. Longitude, though, Europeans had, if they lost sight of land, they had no idea where they were until the late 1700s. On the other hand, that was the H4, John Harrison's final clock to use to establish your longitude. Polynesians navigated across the open ocean for weeks at a time, always knowing exactly where they were. This is a stick chart, and a stick chart is a training aid to help navigators learn how to read the ocean. So just like geographers learn, hopefully, to read the landscape, Polynesians were able to read the ocean. So each of the shells represents an island, and these different parallel lines represent the different swell directions on the ocean during different times of the year. Because what they're actually tracking is, as these swells, the waves that are coming from a consistent direction produced by the trade winds, when they hit islands, they get bent, they change their direction, they travel in a new way. And Polynesians were actually able to read the patterns of waves on the surface of the ocean to find out where they were. So, like I said, those parallel waves, when they hit an island, they slow down as they get near the island, and then they end up going in a new direction. So downstream from the island, you'd find this checkerboard pattern of waves. Upstream, you've got these parallel rollers. So these sticks would represent the pattern of parallel waves during one part of the year, and these sticks would represent parallel waves coming during another part of the year. This is Rincon Point in Santa Barbara. You can see parallel waves up here. As the waves get into the shore, they slow down, they refract, change their direction. And in the open ocean, when they hit islands, they do something similar. So this would be 49 degrees north, 60 degrees east. When you give latitude and longitude, it's always latitude first, followed by longitude. So 49 north, 60 east. Time zones are 15 degrees wide. We're not going to deal with time zones, but you should know how they work. Well, they should be 15 degrees wide. They're really not. They zigzag to avoid cutting up states as best as they can, just like the international date line. So right here, it's Sunday. Right here, it's Monday. If it was 7 o'clock in the morning for reals, it would be 7 o'clock in the morning Monday, 7 o'clock in the morning Tuesday. That this is exactly one day later than right here. The international dateline, as I mentioned, Europeans kept track of where they were all the time. That's how we got those ship's logs. The ship's logs that were made into those maps at some of the early figures that I showed you today. So they kept track in the first circumnavigation of the world. They kept track of where they were literally every second of the day. And they showed up home in Spain and said, wow, it's great to be back here in Spain. You know, it's taken us years to go around the world. It's great to be here on a Friday. And everybody in Spain said, dude, it's Saturday. And they're all, what? No way. We kept track of every minute of every day. And they sat down, they thought about it, and realized, oh shit, we've got to make this imaginary line where it magically becomes tomorrow. So there's two ways that it becomes tomorrow, right? Like if you're in Sacramento and you just stay in the same place for 24 hours, it will become tomorrow, right? But when you travel over the international date line, it's today, it's tomorrow. Or even more confusing, you could fly out of Tokyo Sunday and land Saturday. If it's Sunday in Tokyo, it's Saturday in Los Angeles. Well, depending on the time, depending on where the sunset, the Terminator line is. But if it was noon in Los Angeles, Monday, it would be Tuesday in Tokyo. So, sorry, if it was Monday in Tokyo, it would be Sunday in Los Angeles. It's confusing and mystical. We're not going to spend a lot of time on it. We move on. International Dateline, I'm done talking about that. They moved it to avoid splitting an island nation in half. That's why there's that big weird zigzag. I'm not talking about daylight savings. maps, more maps. So now we know latitude and longitude. That's generally how we locate places, latitude and longitude. Map is a generalized view of an area as seen from above with reduced size and detail. You can't show everything on a map. It's impossible. Cartography is the science and art of map making. Most maps have some common elements. They have a title, north arrow, symbols. The legend tells you what the symbols mean, like this color and this shape means there's this many people in the city, or this color and this shape means something else, or blue lines, rivers, red lines. Is it a road? Is it a county boundary? I don't know. Better look at the legend. And then they'll usually have the scale as a scale bar or a ratio. So I already mentioned that scale is the ratio of the size on the map to the size on the ground. There's 3 ways of expressing scale: as a representative fraction, for example, 1 to 24,000, in which case 1 inch on the map is 24,000 inches. There are no units because the units are the same on both sides. So whatever you pick for the units over here, same units. 1 foot, 24,000 feet. 1 inch, 24,000 inches. Both in the same units. A graphic or bar scale is used when the map might get enlarged or shrunk, or on the web, right? Because you can zoom in and zoom out. Everybody's got a different size monitor, so having a scale bar, a scale bar, is a really good way of showing people what the scale is of that map. And then written scale, they use different but common units. Like 1 inch equals 1 mile, very, very common way of establishing a written scale. Or 1 inch equals 2,000 feet. For a 1 to 24,000 scale map, 1 inch on the map is 2,000 feet on the ground. So they have different units. With a written scale, the units are given on both sides. With a representative fraction, there are no units because they're the same on both sides. So here we've got a 1 to 500,000 scale. So that would be a small scale. And then a 1 to 24,000. Although I'm not sure at what size monitor this would really be a 1 to 24,000. So good thing it's got a graphic scale. Earth is a sphere. Maps are usually flat. Anytime you go from a sphere to a plane, there's distortion. So you can see like all the lines of longitude come together here at the North Pole, but making a globe into a Mercator projection, they have to stretch out to fill in this space, and that creates distortion. Yeah, not my image. Some geographer did this because they were bored. I think it's awesome. They took an orange, painted a map on it, and then peeled it using a scalpel. It looks like a moloid or an interrupted sinusoidal projection. Map projections are how spherical shapes are transformed to flat shapes or vice versa. All maps have some sort of distortion. Either the size or the shape is distorted. Some maps, some projections like the Robinson, they're called a compromise projection because the size is a little bit distorted, the shape is a little bit distorted, but it's overall not too bad in either of those. With an equal area map, the areas are correct. With a true shape or a conformal map, the shapes are correct, but the size is not. Mercator projection is the most common conformal projection. This is a Mercator. So if we compared the shape of Greenland on this map to the shape of Greenland on a globe, the shape would be the same. But if we compare the size of Greenland to Australia, well, like all of these, this square, and I'm assuming this is a 30-degree grid, so going from 0 to 30, 30 to 60, and then 60 to 90. All these lines of longitude should be coming together at the North Pole. They should be coming together to make a point. So all of these should be triangles. Like if I back it up to here, you can see those should be triangles because all the lines of longitude are converging at the North Pole. But because we don't want to have gaps on the map, they have to stretch out that point to 40,000 kilometers. So now the North Pole, which should be a dot, has been stretched out to 40,000 kilometers. So the farther away from the equator you get, the more the distortion of size is. So places by the equator, the size and the shape is good. Places at high latitudes are tremendously distorted. For example, Greenland is about a third the size of Australia. So this is, I think, a Gall-Peters projection, and I just was watching one of my son's, my son is now in his second quarter at UC Santa Cruz, and he's taking an oceanography class, and I thought, oh, I got nothing to do this afternoon. I'll just watch the Zoom lecture for kicks and giggles. And one of the students asked the instructor, do we need to know the names of all these projections? And I realized, oh shit, what a great question. I know why I'm talking about projections. The reason I'm talking about projections is because I want you to know that whenever somebody makes a map, they have a choice to make. Are the shapes going to be accurate or the size is going to be accurate? So if you're looking at demographic data, you're going to want to use an equal, the sizes have to be correct. This map, if it was a demographic like showing population, it would look like there's gajillions of people in Greenland and Canada and Russia, but really those areas are much smaller than you think than they look on the Mercator. And so if you're dealing with demographic data, you're going to use an equal area projection. So that's really it. You should just be aware of that. And as a student, you kind of have to assume that whoever made the maps that we're using, they knew what they were doing. And so if there's demographic data, they chose an equal area projection. But I found a sample quiz question someplace. It was like, what projection is this map? And I thought that's ridiculous for human geography. If you're a cartographer, maybe you should be answering those questions. But otherwise, it's just maps can be equal area or true shape. Equal area or true shape or some sort of compromise. Mercator, it's a garbage map, unless you're a pirate. So it was developed for navigation. If you drew a line from, let's just say, London to Jamaica, and you figured out what bearing or azimuth or direction that was, let's just say, let's say 230 degrees. So you set your compass, and if you sailed in the direction of 230 degrees, you would get to Jamaica. If we plotted out what was a straight line on that map onto this map, it would end up being a great loopy arc, that it wouldn't actually be the shortest distance. It's just because the Mercator map was developed to make navigation easy, it makes navigation easy. If you draw a line on the Mercator, you figure out what direction it is, you sail that direction, you get there, which in the days before good navigational systems existed would have been very important. Tissot's indicatrices. So these circles were developed by a French mathematician named Tissot, Tissot. I was going to say like the expensive watches. So the Tissot's indicatrices, if you drew them on a globe, they would all be identical circles. The size of the circles would all be the same. So on the Mercator, you can see that the distortion is of size. As you move away from the equator, the circles just get bigger and bigger and bigger. So the role of Tissot's indicatrices is to demonstrate the type and amount of distortion from any one projection. So here again, the Mercator, the Eckert-4, which is an equal area map. So you can all the circles have the same area. But you can see this was like oval and weird, and that's like squashed, and that's vertically squashed, or rather, this is horizontally squashed, that's vertically squashed. So you can see that there's distortion to the shape, but the size remains the same. So Eckert was a really good projection to use before some of the other newer, better equal area projections were developed. Oh yeah, this is one of my favorites. This is bad map projection number 358, in which everything is reprojected to be South America. Here's another one of my favorites. This is Argentina. Everything else is Argentina. That's enough stupid geography jokes for now. Just different Eckert-4 versus Mercator. So some of the things that you'll see on maps, we won't use a whole lot of maps with ISO lines. Those tend to be like contour lines on a topographic map showing the elevation of places. Isobars on a weather map, air pressure. So this is a topographic map showing places that are steep because the lines are close together, places the lines that's flat where the lines are far apart, rivers, forested areas, open areas. Forests are green, open areas are white. Places with the contour lines really close together, it's steep. It's a topographic map. We probably will never use a topographic map in class. This is just a map showing the slope, how steep the slopes are of Yosemite. A geologic map, there's no way we're using a geologic map in this class. Some other tools, in addition to maps that geographers use, the Global Positioning System, the GPS, tells you where you are by listening to satellites. Each satellite gives off a signal that tells you what time it was. And the GPS receiver then listens to those signals and calculates how long it took the signal to reach it and then how far away that satellite is. So the GPS receiver figures out where that satellite was and how far away from it is. And then by using a bunch of different satellites, it can triangulate its position. Remote sensing refers to sensing things remotely, as opposed to direct sensing, like touching it, sticking a thermometer into something would be direct sensing. Touching it would be direct sensing. So two types of remote sensing. There's passive. That's just your eyeballs are passive sensors. They just register the energy that's coming in, as opposed to active, like radar and SODAR and LIDAR. They send out energy and then measure how much comes back. So with active, you're sending something out and measuring how much comes back. With passive, you're just receiving energy. And the difference, the active really got important with the development of a technology called LIDAR that I'll talk about in a minute. LIDAR uses laser beams to measure distances. Remote sensing, I'm assuming everybody's seen satellite imagery before. Here's some LIDAR. One of the cool things about LIDAR is the way it works. It actually penetrates through vegetation. And you can put it in an airplane and fly over the jungle. And in an afternoon, you can survey more land like this. If this is the location, I think it is. They surveyed this entire area in an afternoon and found a market plaza, terraced agricultural areas, residential housing. They had no idea that any of that was there because flying over it or walking around on the ground, it's all just jungle. But by using LIDAR, they can strip away the vegetation or they can measure the vegetation. They keep track of the pulses, and so there's the bare ground return and the first return, right? So if you're flying over the jungle, the first return is going to be off the highest things. The last return is going to be off of the bare ground. So they can symbolize that data. Each of these dots then represents a ping of a laser beam that hit something and then was reflected back up to the sensor. And so not only do you get the bare ground, but you can also make 3D models of the vegetation. This is New England. So this is reforested. It had been cleared by colonizers. And these are stone walls that the colonizers made to separate out their land from their neighbor's land. None of which you can see through the forest because you can only see forest. But by using LIDAR, you can strip away the vegetation and see what the bare ground is. So these are two different views of a landslide in Washington. This is the first return off the tops of the vegetation, and this is the bare ground return off of the bare ground. So in the first returns, on the full resolution imagery that you could see on the State of Washington's website, you could actually see individual trees that had fallen down on the surface of the slide. The resolution of LIDAR, because it's laser beams, the resolution is very, 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 very precise. And then the bare ground returns allows you to see previous slides. Like I was amazed. This is just an inset of a small area of the study area of the Oso slide. There's a river down here. just out of sight of this. But up and down the river, you could see evidence of past slides. The whole area is unstable, but because it's so heavily forested, you can't see any of it. But the magic of LiDAR allows you to see all that stuff. LiDAR, geographic information systems, are a means of storing data and combining and analyzing data, making maps. It combines two types of data that's usually stored in spreadsheets, relational databases. Spatial data is combined with attribute data. So those are the two big types of data in a GIS system. Where is it and what is it? The spatial data is where it is. And the attribute data tells you what it is. The data is usually stored in layers that can be combined. So this is a graphic illustration of a landslide prediction model that was developed by the U.S. Geologic Survey. It's a post-wildfire landslide model. So they look at elevation. They take an elevation layer, and from the elevation layer, they can calculate slope. They have another layer that shows, well, upstream burned. So how much of it burned? They're getting that from aerial imagery. Clay content from soil surveys. The more clay, the slipperier the soil is. The more rainfall, the more landslides you've had. The steeper the slope, the more landslides you'd have. So they can combine all these layers and then come up with a generalized risk over 10 years, watershed by watershed. This is in Southern California. You can see these two have the highest risk, and then some of these yellow ones have very low risk. So GIS, again, combines attribute data, high danger of landslides, with spatial data in this polygon. In this polygon, there's a high risk of a landslide. In this polygon, so there's the spatial, the polygon, that area, and then the attribute is low risk. Geovisualization is a way of showing geographic things, but not necessarily with a map. Google Earth, Google Maps, those are geovisualization tools. This is a graphic produced with a geovisualization showing mud flow travel times. So if there's an eruption of, I forgot who this is. I think it's Rainier. If Mount Rainier erupts, when it erupts, it's going to melt the glaciers. The glaciers are going to make mud flows. And in 10 minutes, the mud will be there. 15, 20, 25, zigzag. You got like 25 minutes to get out of Dodge. On the other hand, if you're over here, you got an hour and 15 because it's taking a different path. So it's a geovisualization. You can see that there's terrain. Some things are hidden, but if you live in this area, this might be the best way to communicate the risks to different people in different areas. So maps, I was going to say the biggest difference, I think, is that maps are usually just a vertical view, and this is an oblique or partially side view. Latitude, longitude, map projection, Mercator, Eckert 4, prime meridian. Prime meridian. The last thing I want to say is talking about the cultural landscape. This is a marker that I found in a park in Paris that commemorated the previous, the green line, that until that 1884 International Conference on the Prime Meridian, most countries just used their capital for land-based maps as the prime meridian. So for maps of France, Paris, they used a meridian that runs through Paris as the prime meridian for all of their land-based maps. But for nautical charts, they were using Greenwich because the British were the first people to figure out how to find your longitude. So they were the first people to accurately be able to put longitude on maps, which then resulted in people adopting Greenwich as the prime meridian because that's the language that the maps were in, was using London or just outside London, Greenwich, which is where the observatory was. That's why it's Greenwich. That's where the Royal Observatory was. Just like this line actually ran through the Royal Observatory in Paris, which is just north of where this sign is. And I think that's it for the whole chapter. That's the first chapter. I hope you enjoy it. I hope you find it interesting. I hope you find it not overwhelming. If you have questions, please come to the Zoom sessions. Instructions are in the syllabus. Instructions are on Canvas. And I hope you have a good week.